Gentlemen, today we're going to do some further analysis involving real transformers. In a nutshell, we're going to look at the transformer model in open circuit mode. We're going to have a look at the model on load and essentially, overall, develop a simplified model that can be used on transformers that are loaded as low as 10% of their rated load, and you can still use this simplified model. Okay. The other thing we're going to do is look at finding the model parameters of a real transformer. We're going to do that through short circuit open circuit test. Yep, so we're going to do that on the transformer on the rig there later on. Do a short circuit open circuit test and use that to derive the parameters for the model and try and model that transformer. Okay, so that's what we're going to do today. Did you get set, Joe? So, simplifying the transformer model. The full equivalent circuit for a transformer that we developed last week, where RM and XM represent the the core losses and the magnetizing current required to magnetize the primary side, and that will cause a current to flow even when a transformer is open circuit in the secondary. So that we developed that last week, and then we looked at how the resistance of each winding and what I wanted, the resistance and leakage flux of the primary winding represented by a resistance and an inductance in the primary side, and then the resistance and inductance, leakage flux I should say, of the secondary winding by a resistance and a inductance in the secondary winding. So that's the full model of a real transformer, taking everything into account. However, it's got more detail than you would require to solve most practical problems. It's possible to simplify this model by considering its action, one, when it's got no load, and two, when it's got full load. Okay, so that's what we're going to do now, try and simplify this model a little bit. Okay, so what I've done on the next page is included the full model at the top. Okay, and it's no load, so I've got no load connected. I would have a terminal voltage here across these terminals if I've got a generator voltage connected to the other side, but no current will be flowing either in the secondary or into the ideal transformer. So the current I2 is 0 because T1 is ideal. That means I1 must also be 0. So both of those currents there, as we've already said, are 0. This means that the components R2 and X2 have no effect and they can be ignored. So essentially, these two components can be taken out of the circuit. Yep. Now, the impedances generally of R1 and X1, that's these two here, are so small compared to these ones. If we think that we got an impedance here in series with another impedance there, that's the impedance to that current I0. But in general, R1 and XF1 are so small compared to RM and XM that the R1 and XF1 can be ignored. Because these are going to be, so we're going to see later, these could be in as high as several tens of kiloohms, and those are in ohms. So adding a couple of 3 ohms onto kiloohms doesn't make a great deal of difference. So you can ignore those two. They go as well. That means we get a revised equivalent circuit when the transformer is open circuit, like the one at the bottom. The turns ratio N1 over N2 can be considered to be the ratio of the voltages as well. So we can just do EP over ES, and that's where we come to later on when we look at the open circuit tests. It's a way to get the turns ratio of the transformer. So a simplified version of the model under no load is to just take into account the core losses, because the resistance of the windings and the leakage flux is of no significance. Okay? Everyone all right with that? Now if we consider the real transformer that is fully loaded. So assume we're applying a load Z such that we're drawing all the VA on the secondary side. So we got secondary current times the secondary voltage is at the VA rating of the transformer. Under those conditions, the current IP here is at least 20 times larger than this magnetizing current down that parallel branch. Hence, that current down that the magnetizing branch and the core losses at full load, in terms of everything else, can be ignored. So we lose those two components under those conditions. We end up with a revised equivalent circuit under load, where we've got our R1 and XF1 in the primary side, representing the resistance of the primary winding and the leakage flux from the primary winding, and then we've got R2 and XF2 in the secondary side, representing the resistance of secondary windings and the secondary leakage flux. And it's worth noting that although we're saying this is at full load, it's suitable to use that simplified model of a transformer that is loaded down to as low as 10% of its maximum rated load. So we got a 1000 VA transformer, we could use that model down to it being loaded to 100 VA, 1/10 of what its design loading, and it would still be reasonable to drop those two components under those conditions. Okay? Yeah. We can further simplify that loaded model by shifting or transferring the secondary impedances to the primary side. So as we've done before, we transfer the load impedance over by multiplying it by the transformer ratio squared. We transfer the secondary leakage reactance and winding resistance by multiplying them by A squared. We can also bring the secondary terminal voltage across to the primary side by multiplying that by the turns ratio. We've then got all our impedances on one side of the transformer. We can drop the ideal transformer out of the middle. We've already done some calculations using that model, but what we can also do, a further simplification, is that we can pull the two R's together here and the two reactances together into one resistance and one reactance. They're in series, we can just add them together. It's going to be quite rare that we actually got any particular interest in what the value of these components are. What we're really interested in is modelling how the terminal voltages and primary and secondary currents are going to react to changes in the load on the transformer. But to do that, we need to know what effect these components are going to make, but we don't necessarily need to know separately or work with their individual values separately. What's the point in calculating the volt drops across each of these when we can effectively add them all together and calculate 1 volt drop? Yeah. So furthermore, that model can be simplified down to 1 resistance, 1 leakage impedance, and 1 load resistor transferred to primary side. We can then quite simply calculate what the effect of this is on the current flowing in the primary side, transfer that back to secondary if we want to know the secondary current, and we can quite easily calculate the voltage across the load and so on. And these are the things we're going to want to be interested in. What that current is, and what it transfers to on the secondary side, which we can do by dividing by A. Yeah? Alright, it's multiplying by U. Spot me, did you? Divide by A to bring it across. That's I1 times A. Okay. These two, the two components only need to be separated if you're interested in their values, and you're hardly likely to be. Right? So the significant losses depend on whether we're talking about the thing, we've got this power loss in the core. We can find that out from the transformer when it's open circuit, okay, and we can find these component values out from it being on load, okay. That's what we're interested in, and like I say, the key things we're interested in is what voltages we're going to have. If we put a voltage on the primary side, 1, 2 terminals, what do we get on the 3, 4? And what's the current going to go into load, and what's the power dissipated in it, and so on. We can calculate the power being put in this side and the power coming out the other side, and find the efficiency of that transformer under different loads using that simplified model. But we've got to know what the detailed model is to be able to find ultimately the value of these. So we've got to find out what their separate values are, but then we can pull them together. Okay? Yeah, there it is. So we're going to have a look at a transformer example and find out what some typical component values are. Okay. So for the transformer model shown, it's got a nominal rating of 220 kVA. So you can apply that to either the primary or the secondary and immediately find out what the nominal currents are, because the nominal voltage on the primary is 11 kV and the nominal voltage on the secondary is 400 kV. Yeah. So you're going to use the, if RM is 27.5 kiloohms and XM is 16.5 kiloohms, we're going to use a simplified model to find the open circuit primary current and the power loss in the core. And in the next page in your notes, I've squashed all of this up a bit so you've got some room to do the calculations. Alright? So we're going to have a look, I want you to start having a look at the simplified model to see if we can find out what the open circuit primary current is and what the power loss is in the core. First of all, what we're looking at here, what's the model going to look like? We're talking about when that model is open circuit. So we're going to take away, we can ignore everything to the right of the ideal transformer for a start. So effectively, I'm going to cheat a bit, I am. So we've got a simplified model. We've been able to take out the series resistor and inductance for the leakage and winding resistance, and we can take away everything on the secondary side because we're talking about it being open circuit and therefore no secondary current is flowing. Yep. So how can we find the open circuit primary current? That would be if all there was R, would it? Well, what is RO made up of? It's made up of, it's worthwhile thinking about a phasor diagram here. We're going to get a current, IR, aren't we? Let's move that down a little bit. Yep. And we're going to get a current IL through here, or IF I think that's actually got on there, through that. Yeah. IO, it's the phasor sum of those two. So if we can find this current and that current, we can use Pythagoras to find the total, can't we? Yep. So how can we find IR. Yep, it's EP over RM, 11,000 over 27,500 equals. IF, hang on John. Yeah, IF is EP over XM. That's 11,000 over the, what was it, 16 and a half?
I didn't know you were next jail.
Yeah, I know, it's terrible. A lot of keys on there I don't need. Right, what'd that come out to, boys? 2/3. Who said 1.6? Oh, sorry, I thought you said 1.6, Dan. 2/3 is more. That is exactly 2/3, is it, Joe? 0.6 recurring. Should say 0.7, really. It's one significant figure. Yeah. Well, they are, you know. And I would say that was too much rounding, considering us that small. One significant figure. Yeah, okay. So, now we can find IO, because it is the square root of IR squared plus IF squared. It's the root of only if we're interested in the angle. We're taking the angle into account by the fact that we're doing Pythagoras. But if we're only interested in the magnitude of the current, Joe, we can just do this. So we could, because when you do that polar calculation on your calculator, it's doing these two calculations separately and giving you one answer. It will be doing Pythagoras to get the length of the vector and some trigonometry to work out what the angle is, but it's just doing it all in one go for you. Yeah. So 0.4 squared plus 2/3 squared equals the way to do it, Daniel, is to store that answer and then square it and then add that on afterwards. So carry, although you write down a rounded answer, carry the full answer through is another way to do it, if you're worried about rounding. What we got then? We'll go 0.78. Okay? Of an amp. So that's the current that would flow in the primary side of that transformer under open circuit conditions. What else did I ask you to find? The power loss in the core. Okay? PM. How can I find PM? That's what I'm calling it. How many watts have been dissipated in that core while it's open circuit? If you do, what's current times voltage here? VA. Yeah, if you do that multiplied by the volts, we got the apparent power being delivered to the transformer by the source. Yep, S is equal to volts times amps. We want power. What's going to dissipate power in this circuit? Just the resistor. Yeah, remember, the inductor takes in one half cycle and gives back in the other. No power, no useful power, no heat created by that inductance. All the heat comes from the resistance. So we want the current IR. We can use the current IR and the voltage, or IR squared times its resistance, or V squared over R. Yep. Either of them will do, any of them will do. In this case, I think as you've been given what the voltage applied is, and you've been given the core resistance, you'd probably go with them in this case. So you'd go EP squared over RM. That's 11,000 squared divided by 27,500 equals 4.4 kilowatts. You're looking at a 11,000 down to 400 volt transformer. That's 220 kVA, and we're talking about 4.4 k watts. Okay. Go on by what you've been given. What's the design? Just go back a previous slide, just to show you. We're talking about less than an amp flowing. What is the full load current for that transformer, primary side? How do you get it? S over EP, yeah? So 220,000 over 11,000 is 20 amps. So a primary side current of 20 amps, and that's drawing an amp, less than an amp, when it's open circuit. Yeah, so a fifth, less than a fifth. Okay. And the current on the secondary side comes from 220,000 over 400. I think that come out at 550 amps or something, secondary side current. So it's an end of the transmission line down to 400 volt transformer, yeah, so local site distribution transformer. Okay. All fairly happy with that, yeah? So, second part of the example, for the transformer model shown, nominal rating, we're talking about the same transformer really here, alright, but we're now going to have it on load, okay? So, we got the nominal rating 220 kVA the same, EP 11 kV, ES 400 volts, turns ratio is the same, been given the values of the winding resistances and the leakage reactances in ohms. So if the transformer now is loaded with a resistive load, I kept it fairly simple, I haven't given you a complex load, of 2 ohms, and the generator is supplying the nominal voltage, calculate the primary current the voltage at the secondary terminals ES and the current flowing in the load. Okay, so again I've put a version with that scrunched up a little bit on the next page. Alright, and we're going to use the simplified model, so it's going to be the model with these two removed. Okay, and I'll develop that model on the board here so we can work on that. Just struggling. So look at this problem then. How many of you have transferred all the impedances across to the primary side? So how have you done that then? So if we transfer, first step, transfer all the secondary impedances to the primary side. And the other week we were calling them something like R2 dash. So what is R2 dash? How do we calculate that? A squared times R2. So that's 27.5 squared times R2, 4 times 10 to the minus 3. What do you get? 3.02 ohms. Yep. Second value, x2 dash a squared times x2, 27.5 squared times, what was the value of x? 20 times 10 to the minus 3. What does that come out as? Yeah. And then lastly, ZL dash is equal to ZL times A squared, 27.5 squared times 2 is equal to 2 ohms. Impedance is the load is 2 ohms. On the first page. Let's go back. Transformers are loaded with a resistive load of 2 ohms. What you used then?
I've used nothing, so it wasn't on the second page. So I've been trying to do it without the stuff.
With no load? You're doing a short circuit calculation.
That's where I got myself.
When we do our open circuit short circuit test, we're not going to be applying full voltage to the primary side when we've got the secondary short circuited. That would be disaster. That's what you're doing on a 220 kVA transformer.
No, I was in a load, but I was trying to work out the load. It wasn't on the other page.
No, 2 ohms. So what's the answer to that? 1,500 ohms. Yep. Okay. So now you know those values. Sketch out the transformer model with each of the individual values in, with the ideal transformer removed. So use those values to come up with the modified circuit with everything transferred to the primary side. So having developed that model where all the impedances have been transferred to the primary side and the ideal transformer removed, we can now combine these two and these two into one impedance. Yeah. Well, one resistor and one inductance. So we can combine them together by saying they are 2.7 plus 3.02 Yep. So we can 2.7 plus 3.02 is 13.7 and 15.1 is 28.8. So we now have a transformer model that looks like this. (1510 ohms), 5.72 ohms, 28.8 ohms under load. Yep. So there's our original problem. Find the primary current, find the voltage of secondary terminals ES and the current flow and then the load Z. Can we more ably do that now?
Yes.
Yeah. How then?
We need Z and the resistance.
We can calculate the total impedance, can't we, seen by the generator. Let's call it ZG, because that's the impedance seen by the generator. Yeah? How do I do that? That's equal to 5.72 plus 1510, let's put that in brackets, plus 28.8 J. That's like that in complex, isn't it? Yep. So what we want that, what form would we prefer that to be in, considering that we're going to find I, which is effectively EG over ZG. So we'd prefer that in polar form. So let's have this in polar form. (15) round at the 6 angle degrees. Yeah. I mean, we'll put that there for completeness. Actually, we're not being asked anything about the power factor, so really what we're interested in is the magnitude anyway, this number here. Yeah. So now we can say that I primary is EG over ZG, that is 11,000, isn't it? Over 1516 equals sorry? A lot less than 600 or 700 amps or even 1,000 amps.
I wonder why that's got so lost so bit of that.
Yeah. Okay. So, how do I get the current flowing in the load? What current is flowing in the... How do I do the current in the load? Because I now know that I've got a current flowing here of 7.25 amps. It's the primary current.
Well, do the load resistance multiply the output voltage. So in this case that would be 8.3.
Which you ain't got yet. You ain't got ES. That's what you're now being asked to find. So what can we find? What voltage have we got here? What's that voltage? What do we call that? Careful. What's that? What's that representing? The load transferred to the primary. Yeah, so this is E2 dash. Yeah, we can calculate it here, but to get its real value, actually at the secondary terminals, we've got to transfer it back to the secondary side. Don't forget that. Okay? So, we can calculate E2 dash from, sorry? We don't know ES. Well, ES is what we want to know, isn't it? We're going to find ES. No. That's the nominal ES. Without taking into account these parameters. You cannot do that. You've been asked in the question to find the voltage at the secondary terminals, and that's under these conditions.
Okay.
Yeah? So yes, nominally that's 400 volts, but that's not taking into account the losses because of the fluxes here. So you ain't going to get 400 volts because we're only putting the nominal voltage on. Okay? So we're going to find E secondary dash. How can I find that with what I know? This is 11 kV. There's the current. This is Z dash, isn't it? That's what we call it. So we can find that by doing IP times Z dash, can we not? Yeah. 7.25 times 1510. You're looking confused, Charlie. Sorry? Makes sense to it. It's that imaginary voltage has been transferred to the primary side. We can then transfer it back, can't we? We know it's got to go down, so we know we've got to divide by A. So what did that come out as? 10,000.
Yeah. It's within 200 volts tonight. 947. Yeah,
10947.
yeah. You only got a third of the nominal volts though. Yeah, if you do it properly.
No, remember the nominal primary voltage is 11,000, and we now got 10,947. So we lost less than 100 volts. Yeah. So therefore, ES is ES dash over A. That's 10,947 over 27.5 equals 398 volts. So losing 53 volts on the primary side effectively has us losing just 2 volts on the secondary side. Lastly, the current through the load, IL, ZS over ZL, that's 398 over 2 is
1,000.
yep. So you'd expect 200 amps and you're actually getting 199 amps. Okay. You never know, Keith. You never know. What do you reckon? Why else? Right, gents. We'll just have a look at this, and then we'll take a short break, and we're going to do a little bit of practical work. The example I was trying to build towards the end of the notes, okay. So this just around that. If we want to determine, we could do it with these transformers as well. Actually, determine the transformer's impedance practically. The values of the loss impedances in real transformers, and that's both the core losses and the flux losses and resistances, can be found by practical experimentation. What that involves is, number one, doing an open circuit test. So applying usually the nominal input voltage to the primary side, leaving the secondary terminals open, and measuring the power in, the primary current, and the primary and secondary terminal voltages. Secondly, you do a short circuit test at a lower than nominal input voltage, otherwise you end up with copper everywhere, or blown fuses or whatever, and you do the short circuit test. You measure the input power, you measure the primary terminal voltage, or at least you apply a given voltage, and you measure the primary current. So when doing this, care is needed when performing the short circuit test to ensure that the stated VA rating of the transformer is not exceeded. So we have an estimate of what we're going to apply to make sure we don't go over the VA rating. So in detail then, what that gives you, if we measure those, is what there is on that page. We set the circuit up as up the top, voltmeter across the secondary, voltmeter across the primary, a current, an ammeter in the primary side as well, and a wattmeter, so we can measure the power. So the wattmeter will provide us with the power loss in the core, PM. We can get the apparent power from the measured primary currents and voltages, multiplying them together. We can then calculate from that the reactive power absorbed by the core, because we can use Pythagoras with the calculated apparent power and the measured real power from the wattmeter. We can then use that value, PM, with our applied primary voltage to calculate the value of RM, the resistor in here, this one. And then we can find XM from the voltage here squared divided by the calculated reactive power absorbed in the core. So we've now got values for these two components, and we can get the turns ratio from the primary voltage divided by the secondary voltage. That gives us all the information about the open circuit transformer model. Because remember, we said when it's open circuit, we can ignore the small impedances in here because they are, compared to these two, they are negligible. Alright, so the open circuit test will give us the values of RM and XM. Yeah. We then do a short circuit test. So we put a short across the secondary terminals. We apply a lower than normal EG such that we make sure that too much current doesn't flow in either the primary or the secondary windings. So what I would do there is work out what the nominal maximum primary current is, and then look to apply a voltage so it come underneath that by a small amount, and then you're making sure that your secondary current's not going to go over either. When you've done that, you can get the transformer impedance referred to the primary, so the total impedance seen by the generator from E short circuit, the voltage measured here, and the current flowing from the ammeter. You can get the transformer resistance referred to the primary, the total resistance referred to the primary side, from power short circuit divided by I short circuit squared. And then you can use Pythagoras to get the XP from the ZP and the PM. So the power being measured by the wattmeter. Okay? That allows us to get these two component values. That's the combined primary and secondary side leakage reactances and winding resistances transferred to the primary side. Yeah? Because all the measurement is happening in the primary side, so we cannot even get the individual impedances of primary and secondary from these practical measurements. We can only get that combined value transferred to the primary. But if that means that we can calculate we can put that in a model with a load on and calculate the primary current, that's all we need, because we're only interested in what real current's going to flow anyway. We aren't interested in those individual values. So R is the winding resistance and that's referred are effectively added together. So it's the primary and secondary referred to primary added together. We then got a model of the transformer loaded, so we can take the short circuit out and put a load in once we got values for R and X, and see and determine what the transformer is going to do under a given load, and we'd be able to calculate EP and ES. Alright, we need to do both because we need the transformer ratio from the open circuit side to be able to do anything with that model. Okay, and we probably want to know what the core losses are as well in most instances. Alright? So we end up with a model that looks like that. We can then take this out and put a load in, and we can do some analysis on the circuit. We'll get RA will come from whatever we got on the open circuit test. All right.